So the two common types of energy that we deal with right now, we call this mechanical energy, as opposed to thermal energy or chemical energy, other things we're not going to deal with this quarter. So mechanical energy, energy due to location in a gravitational field, and energy of motion. So let's talk about motion first. And that's kinetic energy. So kinetic means movement, motion. Static means stationary, at rest. Kinetic energy, we use K, and the formula is 1/2 mv squared. 1/2 times the mass times the square of the speed. This is a scalar, and the units are joules. So the total work done on an object is going to tell us the change in kinetic energy of the object. That's our work kinetic energy theorem. Remember, delta is always final minus initial. So this is the final kinetic energy minus the initial kinetic energy. So if the object has more kinetic energy at the end, right, then this side would be positive. So our work done on that object by some other forces would have to be positive. So positive work increases kinetic energy. Okay, so let's look at a quick example. Let's do the cases we had earlier. We had a 10 kilogram block, and it had some initial, what do you want it to be? 1 meter per second. And we pushed on it for, what was it, 5 meters? And that force was 20 newtons, right? And earlier we found the work done. What was the work done in this case? Five times 20 times 1, right? 100 joules, positive. So we expect the block to be moving faster at the end. We know the speed at the beginning, work, and this is frictionless. And what we'll do, the next example, we'll add friction in there. So the work done, the total work done. In this case, it's the only, well, let's draw a free body diagram. This is the work done by F, right? Let's draw a free body diagram for that 10 kilogram block. What's touching it? F. What else is touching it? Surface. Surface can interact two ways, through a normal force and through friction, but in this case, we have no friction. So just the normal force. That's all that's touching it. What can reach in from a distance? Only one thing we know of right now, and that's gravity. I'm going to use mg now because I've got W for work. So I'll just call this mg. Okay, so I just told you it's the total work done, right? The net work done is the change in kinetic energy. So let's find the total work done here. So the net work done is going to be the sum of all of them, right? The work done by F, we just found. The work done by gravity is going to be what? mg times 5 meters times the cosine of 90 degrees, right? So gravity does no work, right? Because it's perpendicular to the displacement. You see that? And the same with the normal force. Work done by the normal force is N times 5 cosine 90 degrees, 0. So we add them up. We get plus 100 joules. And we say that has to equal the change in kinetic energy. It's always cosine. It's always cosine. It's a dot product, and you put the tails together and use the cosine of the angle that the two vectors make when their tails are together, even if it's 3 dimensions. All right, let's plug in some numbers here and figure out what our final velocity is. So what did I say? M was 10. 100, 1/2 times 10 times V final squared minus 1 squared, right? That's 5, that's 20. Is that right? So what is that? Four point something? Okay, so it increased its speed from 1 meter per second to 4.58 meters per second in those 5 meters we were pushing on it. Let's do the exact same push, same block, only on a surface that is not frictionless. And you're going to tell me what mu sub k is. So V initial, 1 meter per second, goes 5 meters. And it's moving at 3 meters per second. And we're pushing on it with F. So same exact situation. F, 20 newtons to the right. It's moving to the right. Started out at V initial is 1, 5 meters. Only instead of moving 4.58 meters per second at the end, it's only moving 3 meters per second at the end. What must have happened? something must be pushing back, doing some negative work, causing it to slow down a little bit, some other force. So in this case, we are going to have friction. Okay, friction there. So we're pushing to the right. If there was no friction, we already did it. It would be moving 4.58 meters per second at the end of 5 meters. But now we know it's not moving that fast, so something else must be pushing in the backward direction, doing negative work. That's friction. So can you figure out what that friction force has to be? And then what mu sub k must be for that surface?